Welcome back to lecture 3. And we completed in the previous lecture data models, conceptual data models, logical data models, and physical models with a complete explanation and details. So in this lecture, we are discussing transactions. First of all, an important question comes into mind why we are studying transactions. So I asked initially why transactions. So two fundamental problems in data management system, and before directly jumping to the distributed data management system, understanding transaction is really important, and it really helps to manage or solve problems. So two fundamental problems in data management. The first one is hardware or software faults. So during the write operations, due to multiple reasons. So the data, partially writes due to electricity outage, or uh, we can say power outage or corruption. So data corrupting, or in multiple cases are there to be the write operations has been disturbed. So that's why it can be partially right or data can be corrupted. So this is one reason why we are studying transactions. So concurrent access conflict, it is really important. As the given example is basically represented in a local context. Okay, so two users reads a certain data. Let's suppose a counter in equals to 0. So this counter both set to in equals to 1. So both right results are is to 1, but should be 2. So this is one of the example, but it is in a local context. Uh, but when it goes to the distributor, so it should be triggered as an alarm that one user has been changed the counter, so the other should know it, and it should be reflected in the databases correctly. Concurrently, every copy of the data should be n equals to 2. So these are the main reasons. So that's why we are studying transactions, why it's important concepts. Okay, so let's start. What is transaction by themselves? So transaction is a sequence of operations treated as an indivisible unit. Indivisible unit because we do not see them. So all operations are happening. So they are get the record in the log file. So satisfying the ACD properties. So last time we also discussed the same thing while we were discussing data models. What is ACID? So ACID is nothing but atomicity, consistency, isolation, and durability. So when we discuss a transaction is a sequence of operations treated as an indivisible unit, but when we call them transaction until unless they satisfy the ACID properties. So here we go with a quick explanation of all of the property of the ACID properties, starting with the letter A, atomicity. That is basically a complete acronym. C, consistency. I, isolation, and D, durability. What does atomicity mean? Okay, atomicity means there are basically all there is a rule all or nothing. Okay, all operation executes or none. Okay, if the operations are executed, so we call them it's committed. If it's not, so we call them abort or roll back them. Consistency, they keep the data integrity. Constraints are preserved before and after the transactions. So they check that the which transaction has been committed. It too is unique and it's certain constraint. We will discuss this furthermore also in more detail. So consistency checks certain conditions, rules, constraints, and uniqueness of the data with multiple formal methods. Okay, isolation. Isolation says concurrent transactions do not interfere with each other's. Like, let's suppose in a database, multiple users are writing at the same time, or readers are reading the data, say, so they do not interfere with each other. This is called isolation. Last, durability. Once committed, results are permanently persistent, survive faults. So once the data has been successfully committed, so it should be long-term persistence and survive the faults. Okay. Atomicity in detail we are discussing now. Okay. Atomicity is one of the important uh, part of the transactions, which is mainly dependent on the log. So a record of all road operation. Road operation means read, update, and delete, plus old values. So old values means the data in the old state, like what was the data before. So start and finish timestamp with the correct information, like timestamps includes date and time, even within the seconds, to check what happens at certain time. Okay, as we said that it's all or none. So I mean all mean it should be committed all or it should be aborted. Okay, so we have two operations here, commit and abort. On commit, operations are applied to data under a lock, so prevent interference. So when we are committing something, so we are applying a log that nobody can interfere. Okay, and or we can say prevent the interference. When a bot log is used to roll back the data, it is pre-transaction state. Let's suppose if a certain operations do not match any consistency rules, so the operation should be rolled back. Okay, so in the rollback condition, it should go back to the pre-transaction state. I mean the old values we have seen in the above, or the data should be in the pre condition. Okay, all of these operations, the database engines cannot solely apply, so they need the operating system support. So POSIX is six standards, okay, which include often, flock, close, and automatic operations. So these are certain types of operations which atomic operations specifically preventing or corrupted data. This is using according to the database engine requirements. So database engine does not only or solely perform all these operations. So this was all about the atomicity. Now let's discuss what is consistency in its implementation. We are discussing the certain acronym and their implementation part both at once. Okay, consistency and its implementation, a property of the whole data management system. We call them system-wide property. Okay, I mean why it is a whole DMS called, because this is really important where the actual in the core part of the query is executing, so they should have to respect the consistency rules and constraint. All component must cooperate. So here, what do you mean by all component must cooperate? The consistency is not something it can be run solely, as in the previous case, they need atomicity, they always support. But in this case, they need the support of the OS and the database engines and multiple constraints in interoperating systems or subsystems they are running in distributed systems. So all of them should be cooperating to take care of this consistency rules and constraints. So we have enforced constraints. Enforced constraints means like uniqueness. The data should be unique. Let's suppose we are running a certain query, so they should have to match their primary and foreign keys in RDBMS. So referential integrity, and they should refer the certain data with the foreign keys, like valid foreign keys, and domain constraints. And domain constraints, their relative data which we are running are either this certain type of data is available or no. So if there is no certain type of data, so the query cannot be run. Okay, so they should have to roll back or abort because the certain type of data is not available. So this is called the enforced constraints, uniqueness, and referential integrity, and domain constraints. So there are some formal methods for the implementations of the consistency. One of them is called horologic, and the second one is automated theorem proving can partially automate the enforcement. So these two are the main theorems which are putting into work through which we are implementing the consistency implementation. So horologics are certain rules which are reasoning about the correctness of a program. Okay, it applies the pre and post conditions that check the the query has been started in the valid state or the database starts in the valid states and transactions guaranteed in also in the valid states. So this is the horologic main idea, and it's basically working on certain mathematical law, mathematical rules. In the automated theorem is basically algorithm, and they check the logic of the query that it does really make sense or no. Like if you see in the domain constraint, they are checking the actual data, okay, in a certain databases. So here the automated theorems are also checking the same thing. It also checks, does it really make sense, what certain constraints we are running or conditions. So both of them can partially automate the enforcement. So this is all about the consistency. Now switching to isolation. Okay, so isolation is as we have seen that atomicity is mainly dependent on a log, and consistency is basically an enforcement constraint, and it is basically working horologic and automated theorem proving. So these are two main things they are implying. But here in the isolation, we are discussing concurrency anomalies. Okay, why, like in the transaction concurrency isolation has been discussed. The reason, because the concurrency is anomalies. I mean, uh, during at the same times there could be certain type of anomalies are happening, so we need to take care of all these anomalies and discuss the uh, idea of the transaction of isolation. So here we have a P1 to P5 codes, and we are discussing uh, what is this and what are the isolation implementation methods. And then we will discuss the isolation levels, weakest to strongest, and at the last, durability. That will be the end of the lecture. So if we see the isolation concurrency anomalies, so here the first one, P1 code, is for the dirty reads. The first three are the reads, dirty reads, non-repeatable reads, and phantom read. And after that, it starts the updates, lost updates, and writes queue. Fourth one, P4, is update, and last two is about writing. So dirty read means T1 reads uncommitted data written by T2. Okay, if T2 aborts, T1 reads invalid data. What does it mean? Let's suppose task one is to read uncommitted information or uncommitted data, which is written by the T2 task 2, okay? But it's still not committed. So that data which has been written by the T2, which is uncommitted, and it is aborted by the atomicity. So in this case, the T1 reads invalid data. So this case is called dirty read. I mean, we have not read the exact data. I mean, which is temporary. You can see that's why they call them dirty. I mean, that information was not relevant. The system now aborted the transaction. So now, see, everything is now connecting. Initially, they are checking their transaction log, either this is okay or not to abort or commit. Then but during the middle they are applying consistency, and here now in the isolation we are seeing their reflection, why we are keeping them the all of the operations separately, or what happens in the concurrency situation. That's why isolation topics or idea or this the need of the isolation comes into existence. Non-repeatable reads. So T1 reads same data twice. Let's suppose T1 reads a certain data twice, so T2 modifies and commits between the reads. Like during the first, okay, you read a certain data, T1 task 1 reads a certain data, in you're reading the same data again, but the first read and after the second read in the middle, I mean the second read has been not occurred, the T2 modifies incommated between reads. Okay, so now T2 is modifying a certain data and it is also commits. Okay, or committed. So we use now defer. So that's why it's called non-repeatable read. What you read before, now it's not the same. So now you read a different thing. The third one is about phantom read. Okay, phantom read T1 runs same query twice. Okay, T2 inserts or deletes rows between the execution. As in the above case, like T1 reads data twice. So here we are running a query twice. Reading and querying is a little bit different. Let's suppose you're applying a certain constraint in conditions to capture the data from the database. So we call them a query. So we are querying them twice. So now T2 comes into the middle. They are inserting or either deleting rows between executions. So you're running query once, but in the middle, task 2 inserts or either deletes rows between the execution. So when we are running the query for the second time, the T1, so it will be a different result set. So this is called phantom read. In the non-repeatable read, that the data is read twice by T1, but here it's twice query. And in the dirty read, there is uncommitted data, and it has been read by the T1, okay? And T2 is trying to commit, but it's aborted. So these are the little bit differences. Last update. What do you mean by last update? T1 and T2 both read a value, then write. Okay, T1 and T2 both reads of values and then writing. Initially they read and then they are writing. One update silently overwrites the other. Okay, so both of them initially read. So after the reading, they are writing. So let's suppose T1 is now ahead of a T2, and in the next time when they are reading, so that will be different thing, okay, or they will be overwritten. So this idea is called lost update. I mean, in the middle the update has been lost, so the other buddy can see a different thing here again, like if you see in the non-repeatable read, but here is it's called lost update. I mean, the update has been finished in the middle, never seen. Fifth P1 code, P5. So write queue is a T1 and T2 read overlapping data. So make a decisions, write different parts, and combine results violates a constraint here. Okay, in the consistency, we discussed the constraint already, okay? So here what is happening, T1 and T2. So read overlapping data. Overlapping data means so like in the above lost update, one of both of them is writing at the same time. So overlapping data, I mean, one time it has been read, in the middle, the another one is writing. So it is overlapped. So they are both initially reading and then they see overlapping data. Make a decisions, write difference. So they are taking a decisions to write different parts. In combined result violates a constraint. So when they are writing to take a decision, so here the combined results violates the constraint. So it will be automatically rolled back. Okay. So this idea we call them a write skew. Okay. Last, which is do not have any code, not applicable. So dirty write. A transaction will write a value written by another uncommitted transaction. So we are overwriting a value written by another uncommitted transaction. And let's suppose T1 writes something, but it's still uncommitted, and T2 tries to overwrite a value which is uncommitted. So this is called dirty write. I mean, which was required to be written, that is not written, but something else. Now, what is the solution for such kind of problems like in concurrencies, anomalies, P1 to P5, and dirty skew, dirty write, sorry. So the first method is log. So read logs and write logs. So in the read logs, I mean, it's a shared, multiple holders are allowed still, But in the writer locks, is it is exclusive. Only one holder is only can write. So a writer lock blocks the reader, and vice versa. In the second solution for this is multi-version concurrency control. This is really important. So in this case, we are maintaining multiple versions of a data. Okay, readers see. So here nobody can block each other's nor read nor either neither writers, so they can see each other at the same time, or they can read and write at the same time. The idea is here we are maintaining the multiple versions of the data. So here the database engines maintaining multiple versions. So if somebody is the same time writing or somebody is reading, so they will see uncertain snapshot without blocking writers or either user readers. So this is how this is working, the control system. The third method, which is really interesting, this is called hybrid locks in plus multi-version concurrency control approaches. Like this is used by modern databases management systems, so which is more high level. So at the below, we are now discussing certain types of the isolations levels, weakest to strongest. We are going from weak to strong. So P1, P2 till P5s are the above concurrencies anomalies. So on the left, we have column, in the left column of level, we have a read uncommitted and read committed, and a repeatable read snapshot isolation, which we call them SI. And then we have a serializable. Okay, we're discussing each and every one step by step. So if we see P1, which is a dirty read, okay, a dirty read, they are allowing, the P1 allows read uncommitted data, P2 is also allowing, and P3 is also allowing. Almost all of them is allowing because there is no lock and there is no multi-version concurrency implementation method here. So that's why all of them are allowing. Okay. In the second one, if you see read committed, so it prevents allow and allow and allow. I mean, the only one they are preventing, that is the P1, okay, P1 code. In the rest of them is allowing. In the reason, in an implementation, so read logs released immediately after the read. Okay, let's suppose read logs, when somebody reads in the after reading, they are releasing their log immediately. So writer logs held to end until the writer portion or not committed properly, that will be held. Okay, that is the reason in the P1 they are preventing them the read committed. And if you see the T1 reads uncommitted data, here the data is actually uncommitted. That's why they are preventing here. So the only one they are preventing here. Repeatable read, almost all of them are preventing, like P1, P2, and P3 is allowing, P4 is also preventing, and P5 is allowing and preventing both. So we will only discuss the prevent, okay? Both read plus write logs held until the end of the transaction. So the main reason, if you see P3 is a phantom reader, so we are queuing them twice, and T2 inserts delete rows between executions, or different results are coming here, and that's why there is a both read and write log, so it's held until the successful transactions. So that's why only they are allowing, and there is no, and the rest of them is preventing. Okay, snapshot isolation, all of them are preventing, only last one is allowing them. Why the other one is preventing? Because there is a multi-version control, concurrency control. So transaction C snapshots from start, conflicts detected, and commit. So last v5 only, which is the right skip, they are allowing, and the reason is because they write a different parts combined results violation at constraint, and that's a rollback. So that's why they are allowing, and they do not follow the multi-version concurrency control. Serializable is nothing. Is I sometimes the fourth level snapshot isolation, also called SI. So now we have a serializable. Serializable means step by step in a sequence. Almost all of them are preventing here, and in this isolation level, it's going from weakest to strongest. The implementation is two-phase locking, 2PL, or serializable snapshot isolation SSI, or the actual serial execution. So this is how we preventing the problems about anomalies of concurrencies, managing with these implementation methods of locks in multi-version control concurrency controls and two-phase locking. In At the end, we can see with the serializable strongest level of the isolation, they are preventing all of them. I mean, all of these anomalies cannot be happened. So, I mean, the important thing was all of them are allowing it. The initial, if you see in the readout commented, all of them were allowing. But as we are moving from the weakest to strongest, so they at the end they are preventing them. So this is nothing but a trade-off again, because there is a major concept. The higher isolation levels provide stronger reliability. I mean, how much you are keeping the isolation very high, so there will be definitely a stronger reliability guaranteed, for not happening the concurrency anomalies. But reducing the concurrency, okay, it also lower your performance of the database in possible deadlocks. Okay, like if we try to reduce the concurrency to not happen, I mean, the reason when we are keeping the higher isolations levels, which we said it provides really a great reliability, okay, guarantee. But the point here it is it reduces the concurrency. Why? In concurrency, automatically lowering the performance in possible deadlocks. And deadlocks is nothing but a two transaction waiting for each other indefinitely. So the main idea is it is a trade-off. If we should have to maintain, either we need such a higher isolations levels, or it should be intermediate. Okay, multi in the modern databases system, as we said, there is a hybrid locks in multi-version concurrency control, so they are using combined. So they are managing this trade-off, how much we need to keep them higher level of isolated from each other, to in the case of concurrency to not reduce the concurrency or proper lowering the performance, okay, and possible deadlocks. So if there is too much deadlocks, it's all not so good that one transaction is waiting for other. So this is the overall idea of the isolation. We discuss concurrency anomalies, then their methods and levels of isolation from weakest to strongest, and their trade-off. Last but not least, it is a durability. Durability, uh, it is committed transaction must be permanently persistent in storage. Okay, let's suppose a transaction is starting from the atomicity. In the atomicity, the transaction is going, so they are directly applying the consistency. In the atomicity, they are recording the log file, and in the isolation they are check the concurrency, is there any concurrency are happening. If it is, they are managing with the isolation methods, and at the end when a certain transaction is completed, so we call them, it should be permanent persistence, and it should be as we see in the previous mm, notes, that when it's committed, it should be persistent survive faults. I mean, they should have to survive the faults now. Okay, use the same transaction log. Okay, we are again going back from the transaction log and on a fault recovery in case anything is happening, and we are recovering a certain fault. As we said, they should be surviving the faults now. So using log to revert a consistent state in then reapplying the committed operations, and we need to see if there is certain type of fault, and either the operation should be go back to the original state, or it should be committed. If they are commit, they are satisfying the conditions of the consistency, and it's okay. They should have to go, and there is no concurrency anomaly, and they should have to be committed. I mean, they should have to be successfully committed and accounted in the log. Otherwise, if there is certain issue with their query or transaction, that should be rolled back again. So this is what durability means. So thank you for listening. Bye.